Okay, class. The next section of the course, or the review, I suppose, is drawing Lewis structures. Now, the good news about drawing Lewis structures is that there's a pretty straightforward process that, if you follow it, it's hard to go wrong. It's not impossible, but it's hard to go wrong. So let's go through this, and then we'll do a couple of examples at the end. Okay, so the first important thing to do is that, and this is probably where the most number of errors takes place, and that is making sure we have the correct number of electrons in our molecule. So we need to determine the total number of valence electrons within our molecule, whatever it happens to be. And you can do that by just totaling up all of the valence electrons and all of atoms that make up that molecule. If the molecule in question's got a positive charge, you need to remove one electron. And if it's got a negative charge, you've got to add an electron. So if the overall structure is -2, that means you need to add 2 electrons. So counting up the electrons is the place where people go wrong the most. It's the second step, which is probably the most challenging of all, and that is to arrange the atoms in a pattern that shows how the atoms are bonded together and connect them with a single bond, with a single line for a bond. So often it's like, well, I don't know how they're bonded together. There are a couple of sort of principles that we can follow which will help you figure this out. The first is that we want to place the atom with the highest bonding capacity in the center. So the good news is for this course, that's often carbon. And remember, bonding capacity is determined by the number of valence electrons. So carbon's only got 4, so it needs to make 4 bonds to get its octet. Oxygen has got 6 valence electrons, so it needs to share 2 more, so it makes 2 more bonds to get its octet. So if you're comparing oxygen and carbon, carbon's got a higher bonding capacity, and the other thing which carbon's got versus oxygen is it's the least electronegative element between the two of them. So the atoms with the highest bonding capacity tend to be the least electronegative. The second point is that the universe tends to like symmetry. So as we're drawing a whole bunch of molecules going forward, what you're going to notice is that they've got quite a high degree of symmetry to them. So if you can arrange the atoms in a way, if one version is less symmetric than the other, then good bet the way that it actually is the more symmetrical version. So keep that in mind. So once you've got your center atom, you place the other atoms around it on the periphery, and you connect it all with a bond. Okay, so the next step is to complete the octet and duets of the atoms bonded to the central atom by adding electron lone pairs. So if it's bonded to a hydrogen, it's set, you don't have to worry about it. But if it's got an oxygen and you've got a single bond, then you've got to add 3 sets of lone pairs to complete the octet. So the next step is basically adding electron lone pairs to the atoms on the periphery to complete their octets. So once you've done that, the fourth step is you need to compare the electrons in your structure to the electrons you started with and see whether or not they match. So in bookkeeping or accounting, if you're debiting one column, you've got to credit another, and they've got to be the same amount. Similar sort of thing here. So we got to determine, do we have the right number of electrons? Do we have too few, or do we have too many? If we have the right amount, then perfect. We don't need to do anything else. If we are missing some electrons, so if our structure is missing some electrons, then we need to add those electrons to the center atom. And if by chance we've got too many electrons, we have to remove some of those atoms from the electron lone pairs from the atoms on the periphery. Okay, and then fifth step, you complete the octet of the central atom. So if your central atom has 8 electrons, your structure is complete, good, perfect. If it has got less than 8, then what you need to do is convert some of the electron lone pairs on the atoms on the periphery into double bonds or triple bonds. So it's sharing it with the center atom and to complete the octet. And finally, you can check your Lewis structure using the formal charge, and then we'll talk about that in a minute. Generally, the best Lewis structures have the minimized formal charge, so there will be, but sometimes there's formal charge built into your molecule anyway, so you got to take that one with a grain of salt. But if you've got two structures and one's got no formal charge and one's got a bunch of formal charge, the best Lewis structure will be the one which has got no formal charge. The other thing which is important is that your electronegative atoms should have negative formal charges if there is a negative charge on your molecule. So just keep that in mind. If you've got an opportunity to have a negative charge on carbon versus a negative charge on oxygen, probably should be on oxygen. I can think of one exception to this, but we'll see if you can ever find it in the class. All right, well, let's do some examples. That's the best way to do this. Okay, so I'm going to share with a drawing program. Share. Okay. So let's start with, say, something like carbon dioxide. Okay, so the first step, of course, is totaling up the number of valence electrons. So carbon has got 4, and oxygen has got 6, but there's 2 of them. So this will equal 12. So our total will be 16 electrons. Good. Okay, second step. The atom with the highest bonding capacity should be in the center. So that's going to be carbon. And we are going to put the atoms on the periphery, which is oxygen. We are going to connect it with a single bond. So I've drawn this in a linear fashion because to me, that looks more symmetrical than if I was to have drawn it like this. And we're going to see a bit later on that, yeah, so this to me looks more symmetrical than that. So this is why I've drawn it like this. Okay, so that's the second step. Third step is we are going to complete the octets of the atoms on the periphery. So do that. So this oxygen's got 2, 4, 6, 8. The other oxygen's got 2, 4, 6, 8. They're both good. Okay, so we've done that. Fourth step, compare the number of electrons. So we've got 2, 4, 6, 8 plus 2, 4, 6, 8, which equals 16 electrons. And this matches that, the same. Okay, so we've got the correct number of electrons. If you look at our structure though, the center atom for carbon does not have a complete octet, right? It's only got 4 electrons. So we need to complete that by moving lone pair electrons to make single or double bonds. So this will equal oxygen. So now carbon has got 2, 4, 6, 8 electrons. Each oxygen's got 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons. So everything's octet is filled, complete. So this would be our final Lewis structure. Okay, let's do another example, which is kind of similar to this. And this would be sulfur dioxide. Okay, so how is this going to be slightly different? Okay, so the first step is we're going to total up the electrons. So sulfur has got 6 electrons. And we've got oxygen, which equals 6 electrons. But there are 2 of them. Times 2. That's 12. So our total is going to be 18. Okay, second step. Put the atom with the largest bonding capacity in the center. So if we're comparing sulfur and oxygen, they're on the same column in the periodic table, right? But the more electronegative atom goes up and to the right. So oxygen is above sulfur, so oxygen will be more electronegative. And so it will have a lower bonding capacity. And we know that sulfur can have the expanded octet. So sulfur is going to be the center atom. We're going to connect it with a single bond to oxygen. And this will be our step 2 complete. Okay, so we need to fill in the lone pairs on the oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now each oxygen's got a complete octet. So we're going to, step 4 is total the electrons. So we've got 2, 4, 6, 8, 2, 4, 6, 8, which equals 16. But this is not the same as our total. So what we need to do is add some electrons to sulfur. So now sulfur, so now we've got the correct number of electrons. We had to add those electrons to the center atom. Now, the fun part is that we have got, does sulfur have a complete octet? Step 6. And the answer is no, it doesn't. So we're going to move some electrons down, and we will have a structure that looks like this. And in this case, sulfur will have a complete octet. Now remember, sulfur can have an expanded octet as well. So the next step is that you could conceivably move these electrons down as well, which would give us a structure that looks like this. And what we're going to see in the next section is we're going to be able to compare these two structures and determine which one is better based upon the formal charge of the atoms involved. But you can see here that the sulfur dioxide is different than the carbon dioxide. And when we do VSEPR theory, we're going to actually see that the actual structure of this compound is different than that of carbon dioxide. So the things that we're going to be doing next is formal charge, which is more electron bookkeeping, and VSEPR theory. Valence shell electron repulsion. Okay, good. Then we will do that coming up next.